So I'll get started and we can talk a little bit later. I know, Annie, I do not have your exams graded yet. There's still a couple people who had to do last minute travel arrangements and the like who still are going to take it. So I am waiting for those final few. Like I always say, I like to grade all of them at the same exact time. That way I don't really know who's I'm grading type of situation. So that's my goal. I'm going to try. Hopefully it'll be done Wednesday, I think. Everyone will be finished by Wednesday, somewhere thereabouts. All right. So we left off. We were talking about relationships between Ka, Kb, and showed that Ka times Kb is equal to Kw. And if you know one, you can calculate the other. We went through a few examples showing how we could, oops, on this previous slide, right, showing how we could take the Ka or Kb and just calculate the opposite from that. Now we're going to go on and discuss a little bit more about kind of some of the acid-base properties of salts. So many ions react. Let me try to get this. Let me see here. Get the laser pointer right. Many ions react with water to create protons or hydroxide, and the reaction with water is often called hydrolysis. So this is something that we have to take into consideration, is that we're looking at ions, right? Ions coming from ionic compounds. They can actually react with the water. When you dissolve an ion in water, it can react, and then it can produce protons, an acid source, or it can produce hydroxide, right, a base source. And that's something we need to take into consideration now. And to determine whether a salt is an acid or a base, you need to look at the cation and the anion separately. So over the next few slides, we're going to be analyzing cations and analyzing our anions and seeing if they have an effect. Can either of these react with water to give us, either protons or hydroxide ions? Let's see here. All right. So when we're talking about the cations specifically, the cations can either be acidic or neutral, meaning that basically the cation can either react with water to produce protons, or it may not react with water at all and just remains neutral. And whereas the anion, on the other hand, can be either acidic, basic, or neutral, meaning that it can react with water to produce acid, protons, react with water to produce hydroxide ions, be basic, or not react with water at all. And we're going to cover examples of each of these. All right. So we'll start with anions. So anions of strong acids are neutral, right? For example, Cl- will not react with water, so hydroxide can't be formed. Think about what this means, right? If we have and I'm going to try using a different pad for drawing, and hopefully my handwriting is a little neater now for everyone. But right, if we have a chloride ion, Cl-, and we try to react that with water, oops, react that with water, and you're looking for an equilibrium to occur. If there was a reaction to occur, you would expect that this would form HCl plus hydroxide ions. All right. This is what you would expect to happen. HCl, on the other hand, is a very, very strong acid, right? This is a strong acid. And the hydroxide is a strong base, right? And we learned that when you place a strong acid in water, it completely dissociates. There is no equilibrium. So this equilibrium arrow that I've drawn here doesn't exist. And conversely, if you were to place a strong base in the presence of a strong acid, you're going to get complete reaction. So the reaction will lie completely on the left-hand side of the equation. And if the reaction lies completely on the left-hand side of the equation, when you add a strong acid, the conjugate base of a strong acid to water, you're not going to form any acid in solution. And thus, any type of anion of a weak acid, on the other hand, when we're talking about weak acids, they're conjugate bases, right? They're basically the conjugate base. Sorry, the anions of any weak acid are conjugate bases, so they're going to create hydroxide in water, right? And so, for example, we take the acetate ion, right? The acetate ion right here, it can react with water, transfer one of the protons, become acetic acid, and that acetic acid is then accompanied by the conjugate base hydroxide ion. So you can see, simply by dissolving the acetate ion in water, we're able to produce small quantities of base in solution. So by producing small quantities of base in solution, any type of anion of a weak acid is going to be slightly basic. So, and then down below it says protonated anions from polyprotic acids can be acids or bases. So now we're talking polyprotic, right? Polyprotic acids, if we had examples in the past, right, where you have, for example, let me think here, draw here, H3PO4, then we have, it can become H2PO4 minus, HPO4 2 minus, and then the PO4 3 minus. Right? So you can see polyprotic acids have the ability, especially these in the center here, these two in the center, can go in either direction. They can end up, reacting with water to form, a stronger acid, or they can react with water to form a stronger base. So depending on which direction the reaction occurs is going to determine whether or not they act as an acid or a base. And the way you're going to be able to figure that out is by comparing the Ka and the Kb. If the Ka is greater than the Kb for the ion, then the anion is going to be acidic, right? Which makes sense, right? You have a equilibrium constant is stronger for the acid, then you end up with an acidic solution. On the other hand, if the Kb is greater than the Ka, right, you have the equilibrium constant for the base is stronger, then the anion is going to be a basic solution. All right, let's go through some examples of cations now. So if we look at cations, so we have group 1 or group 2 metal cations are neutral, right? I'll show you a periodic table a little later when we go through some examples, but when we're talking group 1, group 2, right? Lithium, sodium, potassium, calcium, magnesium, all the ions in group 1 and group 2, they're going to be neutral overall. And the reason for that, if we think about, if we take and dissolve sodium ion, react this with water. Right. We react this with water. In order for this to react with water, you would expect that you would get a sodium, you'd have to react this with water to form either sodium hydride plus, actually that would be, that's not correct. You'd have to react to give, I'm sorry, not sodium hydride, sodium hydroxide plus a proton, which doesn't make any sense, right? You'd have a strong base and a strong acid being generated from a neutral cation. So this reaction is obviously not going to exist either. Polyatomic cations are typically the conjugate acids of a weak base. So for example, ammonium ion, right? So we're talking about the polyatomic ions. right? We had numerous polyatomic ions in the base category. Ammonium is the most common one we discuss for cations, right? And if you take a polyatomic ion, right, if we discussed ammonia before, right? If we take ammonia and we react this with water, we end up with ammonium hydroxide, right? So if you can see here, the ammonium ion is the conjugate acid of a weak base. So if we just simply take NH4 plus and we react this with water, oops, no, thinking ahead. React this with water, we're going to end up in an equilibrium to form the hydronium ion. End up with the hydronium ion plus ammonia, right? So you can see we're basically generating an acid in solution. And so thus a polyatomic ion, a cation, is going to end up being a weak acid. So then we'll talk about transition and post-transition metal cations, and we'll talk about those in the next slides as well, where transition and post-transition metal cations are acidic, right? And then we're going to talk about why, right? If we talk about, we're talking about an iron, right? Iron, oops. For whatever reason, I'm having a hard time here with my little pen. Iron 3 plus. Why is iron 3 plus going to be acidic? Right? There's no hydrogen atom found there. There's no proton. What is it about these transition or post-transition metal cations that make them acidic? So we'll cover that in another slide. So we have some examples down below, right? We have, we look at, let me just change the pointer here. All right. So we look at sodium nitrate. Right, sodium nitrate has a pH of 7. Right, if we go back to the previous slide, right, sodium nitrate is the anion. The nitrate anion is the anion of a strong acid. Right, it's a strong acid, so it's going to remain neutral. And then we look at the salt, the sodium ion. Right, the sodium ion is also a group 1 or a group 2 metal cation, so it's going to remain neutral as well, so we get a pH overall of 7.0. So calcium nitrate, again, the nitrate ion is a neutral anion. Calcium ion also, group 2, it's going to be nearly neutral, right? pH of 6.9 for calcium nitrate. Whereas if we look at zinc nitrate, now we have, again, the neutral anion, but the zinc ions create a pH of 5.5. Same thing with aluminum, it's a group 3, and it creates a pH of 3.5. And the reason for that is shown on this slide here. We have what are known as hydrated cations. So when we're talking about this transition and these post-transition metals, right, you're talking about everything, all of the metals other than group 1 and group 2. So anything in groups, any of the transition metals, the post-transition, the lanthanides, actinides, and group 3, all the metals other than group 1, group 2. And they basically form what are known as hydrated cations, where the water attached to the metal is more acidic than free water molecules, making the hydrated ions acidic. So we're looking here in the center, we have the iron ion. So the iron ion is in the center of the molecule here, and for whatever, and what we're looking at here is, I'm having trouble here with my pointer. All right. So the iron ion here is at the center, and you can see the the water ions have surrounded the iron ion. And by surrounding these iron ion, they have basically created what is known as a hydrated ion. And all it is the iron is in the center. It's being stabilized, right? The iron has a 3+ charge on it, and that 3+ charge overall isn't very stable. So by donating electrons, you end up in a situation where the oxygen atoms are donating their lone pairs to that central iron atom, and they stabilize the 3+ charge. But when they do that, what happens is it weakens these OH bonds. So these OH bonds end up being a little weaker, and by being a little weaker, they can then react with neighboring water molecules. So this neighboring water molecule reacts with one of the protons here. It creates this new iron-oxygen bond, right? It's no longer a hydration bond. The iron atom, the complex goes from a 3+ to a 2+, because we've transferred one of the protons to a water molecule and formed the hydronium ion. Right, so you can see down below what's going on from a chemical equation perspective. The iron here is hydrated, has 6 water molecules attached to it. A water molecule reacts with this. It pulls a proton off of one of the water molecules that are the hydrates. So you can see now the iron remains with 6 hydrated ions, and now has 1 hydroxide ion. The complex goes to a 2+, and you form the hydronium ion down below. So when we're thinking about this, you can see by simply dissolving iron 3+ in water, we form a hydrate, and that hydrate can react with water and make an acidic solution. So each of these individual transition metals and post-transition metals have an acidity associated with them. And that's what we see, some of the Kas of the individual hydrated transition metal ions. So you can see iron 3+ has an acidity of approximately 6.3 times 10 to the minus 3. Right, so this is, we're talking about the iron 3+ is a relatively acidic proton, right? It's a weak acid, but it's on the stronger side of weak acids. Right? Chromium 3+, 1.6 times 10 to the minus 4. Right? Aluminum, right, 10 to the minus 5. Iron 2+, I find this interesting, right? An iron 2+ is actually a weaker. And think about what this means, right? You have a smaller charge. A smaller charge is going to be less attractive towards the hydrated water molecules, and it ends up having an overall weaker acidity. The zinc 2+, right? Zinc 2+ also down at 10 to the minus 10, nickel 2+, 10 to the minus 11. So you can see the 2+ ions tend to be weaker acids. The 3+ ions tend to be stronger acids, which makes sense, right? As a larger charge has a greater attraction towards the partial negative charges of the oxygen atoms. A smaller charge has a weaker. So here's the general rules. So when you're trying to figure out whether or not you have an acidic, basic, or neutral solution when you dissolve a salt, you have to look at both the cation and the anion. So, let me just write that right down. Basically analyze the cation and the anion. Right, so if you analyze the cation and the anion, then the question is, what type of anion or cation do I have, right? So if we have a group 1 or group 2 metal cation, right? Group 1 or group 2 metal cation, right? We're talking about in the periodic table, we have group 1 or group 2. Right? Any of these, group 1 or group 2, we're going to have a, overall neutral molecule from the side of the cation. We have the strong acid, right? A strong acid is completely dissociated. There is no equilibrium. So if you're taking the conjugate base of that strong acid, right? The conjugate base, let me just write that down here. Okay, so what we're talking about when they say the anion of the strong acid, what they really mean here, right, is the conjugate base. Right, the conjugate base of that strong acid. Right, you take the conjugate base of the strong acid, and that conjugate base is never going, it's not in equilibrium with the acid, so it's going to remain neutral as well. Right. So the second example here, if we take now instead and we look at the group 2 metal cation, so we know this part is going to be neutral, and we place this with the anion or the conjugate base of a weak acid. Right, the conjugate base of a weak acid we know is in equilibrium with the acid, right? And therefore it's going to be basic, right? This is going to be a basic solution because this anion is going to react with water to produce hydroxide ions. We talked about that earlier, right? We have the anion reacts with the water and produces OH minus. So it's going to be basic. So the anion ends up basic. You have a conjugate base of a weak acid. Right. And then we have a post-transition or transition metal cation, right, or some type of polyatomic cation. We know that this, when we react these with water, they are going to form acidic solutions. If we combine them with the anion or conjugate base of a strong acid, right, this produces a resultant neutral solution. We're going to end up with this acidic overall solution, right? So you end up with an acid, and that comes from the fact that we have this transition or post-transition metal cation. And we'll go through some examples of this, right? So the cation dominates in this case. The last example is shown down here, and I'm having a problem here. Right, the last example down below is the transition or the post-transition metal cation, or this polyatomic cation, right? This produces an acidic solution, and we couple this with the conjugate base or the anion of a weak acid, which produces a basic solution. So you have opposing forces going on here, right? One wants to produce an acid, the other one wants to produce a base. In order to figure out which is which, we have to compare the Ka and the Kb, right? What's the Ka of the polyatomic ion, the cation, or the transition metal? Or what's the Kb of the conjugate base of that weak acid? And whichever one is greater is going to dictate whether it's a acid or a basic solution. Okay, let's go through some examples. All right. So these are going to be chemical formulas of 5 ionic compounds or salts that are going to be given, right? So we're talking about 5 ionic compounds, right? Here, just realize we're talking about salts that are going to dissolve in water. And we're going to identify the ions in solution and assess how each ion will affect the pH. So we're going to walk through, and then we'll go with the first example. We have barium acetate, right? Barium acetate. So this solution contains barium ions and acetate ions. And the barium ions, the cation is an ion of a heavy alkaline earth metal, right? So that's going to be a group 2 metal, right? Group 2, we all know, is not going to affect pH, right? Group 2 metals don't have no effect on pH. The anion, the acetate, is the conjugate base of the weak acid, acetic acid. And it's therefore going to hydrolyze to produce hydroxide ions, thereby making the solution overall basic. All right, so what they're saying here is, when we try to, if we draw this out, we have barium 2+ ions, and we try to react that with water. You can see that essentially there is a zero reaction occurring here. So the barium isn't going to form an acid or a base. It's not going to form an acidic solution. Whereas the CH3 COO minus will react with water. Right, this will react with water and form an equilibrium to give us acetic acid as well as hydroxide ions. I'm going to draw you're going to see it eventually drawn in organic chemistry as HO minus. Oops. Having problems here where this keeps having some troubles here with my little pen at the edge of the screen. All right, so you can see it drawn both ways. All right, you're producing hydroxide, and hydroxide is a strong base, but we're going to produce small quantities, so we're going to make a basic solution. Right. And we have ammonium chloride, right? And ammonium chloride, in the case of ammonium chloride, we're going to get my laser pointer. Right, we have the ammonium ion. The ammonium is the conjugate acid of a weak base, and it's therefore going to be acidic, right? We have an acidic proton. So when we'll go through what that looks like. And the chloride is the conjugate base of a strong acid, right? Strong acids completely dissociate, so therefore it's not going to have any effect on the pH of the solution. And because the solution contains an ion that is acidic, and one that has no influence on pH, the ammonium chloride solution is going to be acidic. Right, so let's go through and draw out those reactions, right? So we have our ammonium ion. Right. And the ammonium ion is going to react with water, right, in equilibrium to give us ammonia plus the hydronium ion. So you can see we produced a strong acid in solution, so we're going to produce an acidic solution. Whereas the chloride, you try to react it with water and look for an equilibrium, has no equilibrium. So with no equilibrium, you're basically, the only effect you're going to observe is coming from the ammonium ion, so we have an acidic solution. All right, then we have methyl ammonium bromide. Right, methyl ammonium bromide. So in this example, the CH3 NH3 is a positively charged ion. So some of you are probably looking at this and trying to remember where this came from. So CH3 NH3, and I'm trying to get to the pen here. Right, so we have a here. Right, so we have CH3 NH3. It's going to look like that. It's like this, right? Where you have a positively charged nitrogen here. Right. This looks just like ammonium ion. The only difference is we've replaced one of the hydrogens of the ammonium ion with a CH3 group. Right. So this is an organic base, the conjugate acid of an organic base, the methylamine. Right. So in this example, you can see here, right, the ammonium ion is the conjugate acid of a weak base, right? The CH3NH2 is an amine. Right? The only difference between CH3NH2 And NH3 is, again, one of the hydrogens has been swapped for a CH3 group. Otherwise, the NH2 and still has a lone pair on it that can act as a base. So therefore, this CH3NH2 is an acidic substance, whereas the Br minus, the bromide, is the conjugate base of a strong acid, HBr. So therefore, it's going to be pH neutral. Because the solution contains one ion that is acidic and one that has no influence on the pH at all, then the solution of CH3NH3Br was going to be an acidic solution. So I'm going to draw out the steps equilibrium again here. So if we have CH3, NH3 plus reacts with water, and forms methylamine plus the hydronium ion, which is a strong acid, right? So we form this acid in solution here, whereas we look at, again, a weak base, Br minus, and we say, is this going to react with water? And we go to draw the equilibrium, and we say, no, this will not react with water, right? Because in order to react with water, you would have to form HBr, which would be a strong acid. So we know the equilibrium would lie completely to the left-hand side. So there's no equilibrium here. All right. Last example, we have potassium nitrate. And potassium nitrate now, we have, this is not the last example, I think there's one on the next slide. Right, we have potassium nitrate, and this solution is going to contain the potassium ions, right? It's a group 1 ion, and it's therefore going to be neutral. And then it has the nitrate ion, and the nitrate ion, which is a conjugate base of the strong acid HNO3. Right, I have on the next slide, right, you can see HNO3 sitting at the top here. Right, HNO3 is one of the strong acids, and therefore, since it's a strong acid, the conjugate base, NO3 minus, is going to be neutral as well. So neither of the ions are going to react with water to any appreciable extent, making the solution overall neutral, right? So if we draw out, again, the individual steps here for understanding, right, we have our potassium ion. We try to react that with water, and we're going to say, is there a reaction that will occur? And the answer again here is no, it will not occur, right? Because you'd have to form potassium hydroxide and a proton source in acid, which obviously the reaction would lie completely to the left-hand side. And the same thing here. The nitrate ion, try to react that with water. And you can see here, in order for that to happen, you'd have to have HNO3 being formed, a strong acid, right? HNO3. And we know when HNO3 dissolves in water, it completely dissociates in solution, right? And additionally, you'd have to form hydroxide ions. And hydroxide ions are strong bases, so these are never going to be formed in this particular solution. One last example, aluminum chlorate. And, right in this example here, the laser pointer again, right? The solution contains aluminum ions, right? Aluminum ions and chlorate ions. Well, the aluminum ions have a charge of 3+ or higher. Anything with a 3+ or higher is going to be acidic, right? You're talking about, this is not a transition metal, but it's a group 3 metal. It's going to be an acidic overall. The chlorate ion is the conjugate base of a strong acid, HClO4. It's not in this table, but we will learn a little bit about these types of polyatomic ions and having multiple oxygens in the next few slides. And you'll be able to recognize that anything with 4 oxygens is going to be an extremely strong acid. So this is a strong acid. We're telling you that. So therefore, it's going to be just like the last example. This ClO4 minus is going to have no effect on pH. Thus, the acidity is going to come purely from the aluminum ion, right? Just like the last example. Let me go through the example here, where we have the aluminum in the 3+ state is going to react with water. And in this case, it's going to react with water to form these aluminum hydrates. And it's, I'm going to put an X in the front here. And this is going to form, we don't have to know at this point in time how many hydrates there are, but they're going to be multiple hydrates that continue to give us this 3+ charge. Then you're going to react this with a water atom, right? And this will react with a water atom to give us our aluminum hydrate X minus 1 times the OH minus, makes the OH. And this is all going to have a now 2+ charge. And it's going to give us oh, that's not a 2, that's a 3. It's going to give us acid in solution. So the key is when we have any transition metal or group 3 metal, anything larger than group 1 or group 2, we're going to react with water molecules. We're going to form a hydrate, and this hydrate can then react with an additional water molecule to give us the hydrate plus the hydroxide with a 1 less charge and generate some acid in solution. So we end up creating an acidic overall solution. Anybody have questions on any of these parts? I've been babbling on for a while and I haven't seen any questions popping up in the text box. We're going to do sample problems before in the next step. So before I send you off to work on the sample problem. No questions? All right, so let's take the time and work through a sample problem. There's a sample problem here, right? It's the one that says, order the following solutions from lowest to highest pH. And it gives you 3 solutions, right? Let me change this slide here. So we're talking about here's the problem. So here's the problem set right there on the screen. So to tell whether it's a strong or a weak acid, you just look at the chart. Yes, correct. We're going to have a chart, and you're going to, look at the chart to determine whether or not it's a strong or a weak acid. You're going to be looking at the Kas or the Kbs, right? And obviously, the strong acids in that table at the top of the chart are all going to be completely dissociated, so there's no Ka for those. And anything that has a Ka is just going to be a weak acid. So therefore, its conjugate base is going to produce a basic solution. All right, so here's the example. All right, you're going to be ordering the following solutions. So you need to analyze each of these, right? You have a 0.1 molar sodium hypochlorite solution, a 0.1 molar potassium bromide solution, and a 0.1 molar ammonium perchlorate solution. So which is going to be acidic? Which is going to be neutral? Which is going to be basic? Are all of them acidic or all of them neutral? So think about what you're generating in solution here. Break down each individual ion and look at the individual ions and try to determine what they form. Right? I'll give everybody a second to think it through. While you do that, I'm going to take attendance of tardy folk. Let's see. Ooh. All right, you see a couple people still. If you're all looking at these problems and these examples, you're probably wondering, okay, what type of solution do I have here? Right. So in the first example, you have sodium ions. Sodium ions, and you have hypochlorite ions. Right. Sodium ions, I want to get some votes. Let me get the text box up over here. Right. So is the sodium ion going to be acidic, basic, or neutral? So type A, B, or N into the text box. What do you think? A, B, or N? Got a bunch of N's and a bunch of people refusing to type. Their fingers are broken. All right, so it's going to be neutral, right? So we have the sodium ions are going to be neutral. Right, you're going to be neutral here because it's a group 1, right? This is a group 1 metal. So group 1 metals are going to be neutral. All right. The ClO minus, the hypochlorite ion, is that going to be acidic, basic, or neutral? A, B, N. What do you think? Get one brave soul. Everyone else is just guessing, trying to think through. If we react, we were to draw out the reaction, we react this with water, what's going to happen? Right, you have a negative charged substance reacting with water. Right. You end up with HClO plus the hydroxide ion, right? And the question is this a strong acid or a weak acid? And we don't have it in the table down below, but if you look back in the table or think back to the table in the PowerPoint slide, this is going actually in the weak acid table. So this is a weak acid. And because this is a weak acid, that's a weak acid there. Fix that handwriting. All right, so we have a weak acid here. So if that's a weak acid, would ClO minus be a weak base, strong base, a non-base? Does everyone think now? All right. That's going to be it'll be a kind of a weak base, probably somewhere in between. Strong bases, we'll show you some strong bases a little later. But weak acids generate weak bases typically. So you can see, right, we've generated hydroxide ions. By dissolving ClO minus in solution, we generate hydroxide ions. So this is going to be basic. Right, so overall, when we take into account both of these, we're going to create a basic solution. All right, the next one, we have potassium ions, and we have bromide ions. I want people to vote again. So you have potassium ions and bromide ions. Is potassium going to be acidic, basic, or neutral? So for those of you who might not be understanding, is there a question? Do you not understanding where is potassium on the periodic table? It has a +1 charge. You might need to look at the periodic table. And I wish I could switch in between slides. So potassium's in, if I told you potassium was in group 1, right? And so this is in group 1. Right, so if it's in group 1, therefore going to be neutral. Right? And because of, additionally, you can see because it has a +1 charge, it's also not going to form an acidic solution. So what about bromide? Bromide, acidic, basic, or neutral? You take bromide and react it with water. Is HBr a strong acid or a weak acid? What about all of the, it's a strong acid, right? HBr is a strong acid, right? It's one of the halogens. All of the halogens except for fluorine, right? So chlorine, bromine, and iodine all form strong acids. So if you're forming strong acids, then HBr is a strong acid, so this is completely dissociated. So this equilibrium doesn't exist. The reaction lies completely to the left-hand side. HBr completely dissociates, so it's not able to be in equilibrium. Anybody want to change their votes? So acidic, basic, or neutral? So correct, because Br minus, right, so is a strong acid, a conjugate base of a strong acid. We're therefore going to end up with a neutral solution. So because of that, because they're both neutral, we end up with a overall neutral solution substance here. And we have our last one. We have the ammonium ion. And we have our perchlorate ion. Right. So is ammonium ion acidic, basic, or neutral? Right. This is our polyatomic ions. Right. If you have a lot of people not answering at all, Is it because you just don't, you're the group that don't like to raise their hands at all, or you're not understanding? If you're not understanding, please ask questions so I can help clarify. They said nice. I guess once you're far enough down the list, you just don't want to guess, and then you look just like you're saying what everybody else said. Right, so it's going to be an acidic solution, right? So this is going to be acidic. Right, it's an acidic solution because the ammonium ion, right, ammonium ion reacts. Right, it's going to react with water to form ammonia plus the hydronium ion. And this hydronium ion is acidic, right? So we basically created an acidic solution. Now we have the perchlorate ion. Now I know this is the one that I talked about on the last slide. It's not in that table of strong acids, but it's the conjugate base of a strong acid. So if it's a conjugate base of a strong acid, is the perchlorate ion going to be acidic, basic, or neutral? Running out of space here. Right, ClO4 minus plus water. If you were to draw the equilibrium, would form HClO4 minus plus. Oops, no minus there. This hydroxide. All right, so you generate a strong, that's a Cl. You generate a strong acid, so this equilibrium doesn't exist because strong acids completely dissociate. So therefore, you're right, you're going to end up with a neutral. And then when you can combine an acidic with a neutral, you end up with an acidic solution. So if you need to go from lowest to highest pH, I need votes, lowest to highest pH. So when you're talking about pH, I would give votes A, B, C, D, or E. A bunch of E's, correct, right? So the lowest pH is going to be the acidic solution, right? So that's going to be 3. Highest pH is going to be the basic solution, which is 1, and obviously 2 ends up in the middle. All right. Questions on that? Goof? Does that mean complicated? Or you made a mistake? Too early for this? That means it's always too early for this. Time hasn't changed. All right, back to the PowerPoint. The next problem, sample problem. So we're gonna take it up a notch. So the last example was pretty straightforward, acidic, basic, or neutral. Now what happens when we have a compound that's amphiprotic anion, right? An amphiprotic anion means it can act as either an acid or a base. So it's one of these polyatomic ones. So this example says, predict whether the salt Na2HPO4 forms an acidic solution or a basic solution when dissolved in water, right? So for that, we have to evaluate each ion, and we're going to predict whether it's acidic or basic. And then right? We're going to look at, first of all, the sodium ion is cation in group 1A, so it's not going to affect the pH at all. So all we have to do is analyze whether or not the HPO4 anion is going to be acidic or basic, right? This is the only, this group here is going to make the decision as to whether or not the solution is acidic or basic, right? So it can act as both an acid and a base, and we're going to draw, right, as an acid, if we take the HPO4 and it can dissociate to give us the H plus the PO4 ion, right? And remember, I told you we've been transitioning over, right, where in the past we would draw it out this way, where we would have HPO4 this would react with water, and we get an equilibrium that would look like this, where we have H3O plus the PO4 So you can see now we've started leaving out the water. The water is being left out now, where we're just simply looking at the dissociation of the ion itself. So we have the ions dissociated to just give us the protons plus the conjugate base of the acid. Right. And then we have in the next part of the example, right, where the HPO4 can act as a base, and that can react with the water molecule, and it generates the conjugate acid of the base, right? It's acting as a base, so we generate its conjugate acid, H2PO4-, and hydroxide ion, right? So you can see when it acts as an acid, it generates acid. When it acts as a base, it's generating base in solution. So in order to, what we then need to do, we have two different reactions. We now have to look at the equilibrium constants of each of these reactions to determine whether the solution is acidic or basic, right? So we got to get the equilibrium constants of each of these reactions, right? And the first one is going to be a Ka, and the second one is going to be a Kb. So we pull up the table down below, right? We have our table down below, and we can see if we look at the phosphoric acid, right? So the table just gives us phosphoric acid, H3PO4. You can see that our ion isn't shown in the table down below, but you do need to recognize that H3PO4 dissociates, right? It dissociates to give us, and I just want to make sure you guys understand, right? We have H3PO4, right? H3PO4 will can dissociate to give us H2PO4. I don't know why it does that. H2PO4 minus. It can also give us HPO4 2 minus and PO4 3 minus. So in order to get, you can see there's a Ka associated with this step, Ka1. There's a Ka2 associated with this step, and then a Ka3 associated with that step there. You see there are 3 Kas, and when we're looking at the table here, right, we have 3 different Kas. Let me erase that and get it out of the way. So with 3 different Kas, we need to figure out which are we going to be interested in here, right? So we're looking at the HPO4 2- ion, right? HPO4 2-. The Ka for the first step, right here, right, is going to be Ka3. Everyone see that? So we have Ka3. Any question? Is it more likely to be a base, though, because the charge on PO4 minus, no, 2 minus. It's, well, we're going to try to figure out, it depends purely on the, oops, sorry, it depends purely on the Ka here going in this direction. So Ka3 versus, we're going to look at the Kb going in the opposite direction. Okay, so since we're only dissolving one ion, we're not going to be looking at the PO4 3 minus. PO4 3 minus is going to be formed in solution, right? All we're interested in determining whether or not it's an acid or a base is how it acts. So we're going to look at Ka3, but the other part that we need to calculate and we needed to figure out, and we're going to need to figure out on the next slide, is if we look right, in the opposite direction, right, we have the Kb, I'll call that Kb2. Right, Kb2, right, we have the base dissociation constant going in the opposite direction. Does that make sense? Did that answer your question? Or did I not understand your question? Hello? All right. I'll assume yes. All right, let's look at the next slide, right? So if we take a look here, we have the Ka, right, for the acid equation, right, the Ka3, right? We pull that off the table. That's just down in the bottom corner here, right? But we have Ka3. That's just 4.2 times 10 to the minus 13, right? That's our Ka2. Well, you can see here, for the base equation, the Kb isn't in the table, right? In order to figure out the basicity, the base dissociation constant for HPO4 2 minus, we only have its Ka for that step, right? And we know this is the Ka going in the for its conjugate acid. So we need to determine, we look at its conjugate acid, the H2PO4, and we then take and calculate the Ka times Kb equals the Kw. Now I want to point something out to all of you, right? If we go back a slide, right? We're trying to determine what this Kb2 is here. And recognize what we're doing on the next slide. What we're trying to do is, we need to look at the conjugate acid of this, because it's acting, the HPO4 2 minus is acting as the base. In order to figure out Kb2, we have to analyze and look at the conjugate acid of that base, and we need to get calculate the Kb from that acid, not from the Ka3, right? We're not looking at the ion itself. We're looking at its conjugate acid, one step back further, in order to determine what the acidity is. So when we go through the calculation, you can see here that we're pulling a number. Go back to the laser pointer, right? The Ka2 that we're using is this second one, 6.2 times 10 to the minus 8 is the Ka2 that we're going to use for the calculation. Right? And therefore, when we do the calculation, right, we have our Kb of the base that we're talking about times the Ka of its conjugate acid is equal to the Kw. We simply plug in, right? We don't know the Kb here. We do know that the Ka is 6.2 times 10 to the minus 8. We plug that into the equation, so we have 1.0 times 10 to the minus 14th divided by the Ka gives us our Kb of 1.6 times 10 to the minus 7. So the next part is simply to compare these two, right? We compare the Ka times the Kb and the Kb, and we see that the Kb is a larger number, so this is going to be a basic solution. All right. So you can see here, obviously, I'm running over a couple minutes, sorry. You can see we end up with an overall basic solution here because this amphiprotic anion ends up with a stronger Kb in solution. Okay. Any questions before we sign off? Otherwise, we'll pick up with a sample problem at the beginning of next class. Questions? Otherwise, have a good week, everyone. If you're going to be traveling at all, stay safe traveling. For those of you who are still on campus. All right. See everyone.